Welcome to the course Introduction to Algorithm. My name is Saurabh Mukhopadhyay. I am a faculty member at IIT Kharagpur. I will be lecturing this course, and this is the first lecture of this course, Lecture 1. In this lecture, we will discuss sorting algorithm. Mainly, we discuss two sorting algorithm, insertion sort and merge sort. And we will discuss their time complexity, that means the run time, how much time it will take to sort a input, and there we will discuss the asymptotic notion of time complexity, and we compare merge sort and insertion sort based on the time complexity. So, let us start with the what do you mean by a sorting problem. So, in sorting problem what we have given a sequence of n numbers a1, a2, an, and we need to sort it. That means we need to find the permutation of this number, rearrangement of this number a1 prime, a2 prime, an prime, such that they are sorted. So, for example, if you have a number 8, 2, 4, 9, 3, 6, if this is the input, then our sorting algorithm should give us the output as 2, 3, 4, 6, 8, 9, sorted one. So, that is our output should, that is our algorithm should output. So, given any input of n numbers, usually they are integers, we should, our algorithm should able to sort them. So, the first algorithm we will discuss is insertion sort. So, insertion sort, this is the pseudocode for insertion sort. What is the input in this is sorting algorithm? So, input is n numbers, and these numbers are typically is an array, a array. So, we have an input of n numbers in a array. This array is a array which is starting from 1 to n. So, this is indexing is 1, then we have a second index 2, and then finally this is ending with the n. So, this array is starting from 1 to n, and we have n numbers in this array. So, that is the input, and we need to sort that numbers. So, what we are doing over here, the code, we are having a outer loop in j. So, this is a for loop in j. So, j is the index which is starting from 2 to n, and what we want in this jth loop, the loop invariant, we want wherever j will be pointing, before that the array should be sorted up to j. I mean up to here the array should be sorted. Now, we want to find the position of this element aj, where it should be inserted. So, why we starting from j is equal to 2? Because for j, if we start for j is equal to 2, then the before that we have only one number which is a1, and one number is already sorted. So, that is why we can start with j is equal to 2 to n instead of 1 to n. Okay, at some point of time j will be pointing somewhere in the array. So, what we are doing in this loop, jth loop, we are storing this aj value in the temporary variable key. So, we take a temporary variable key and we are storing this value aj. And now we know that up to this, I mean up to j minus 1, this sub array is sorted. So, we take help of another index I, and I is basically the I is the this one, this is ith index, I is j minus 1. So, I is j minus 1. Now, we compare these two values basically. If this key value, if aj is greater than this, so suppose this is 7 and this is 9. If aj is 9 and this is 7, then we can increase j by 1, and that will be taken care by for loop. We do not need to do anything over here, and still we can have this loop invariant that then that this will be new j, and up to j it is sorted. But problem will occur if this value aj is less than this ai. So, that means if the key, if the value over here is less, if suppose this is 6, so we have a sorted sub array whose maximum is 6, and now suppose this is say 3. So, we cannot increase j by 1, because if we increase j by 1, then we have a subarray up to this which is not sorted. So, basically we need to do something when that situation occur, when aj is less than this value, then we have to find the position of this aj in this subarray. So, for doing that we do this while loop, we will do this while loop. So, we check whether I is greater than 0 or not. If I is equal to 0, that means we are at the end of this, then we can insert this in the beginning. So, that is the condition for I is greater than 0. This is a ANDing, so both has to satisfy. If the both condition is, this is logical condition, if both value is 1, that means if the both condition is true, then only we go to this loop, this while loop. Okay, so this condition is telling if the key value is less than this ai, then we must do this. What we will do? We shift this value here, that is by this instruction ai plus 1, ai will be copied to ai plus 1, whatever value will be here will be copied here. So, but we have already stored this value in key, so there is no worrying about losing this value. And then we decrease I by I minus 1 to check whether this key is still less than this value or not. If this is not, if this is greater than this value, then this loop will not enter, and we will just I is this one, we will put the key value over here, that is ai plus 1, the position we will put the key value. But if still it is less than, if the still key is less than I, this is the new I now. So, this is our new I. We compare these two now. If this is still less than, then we have to again shift it here, and we have to keep on doing until we reach to the situation where the key is greater than, we can insert that. Otherwise, if we reach to the beginning of the array, it may happen that we already reached to the beginning of the array. So, this is the loop invariant for the jth loop, and this will continue up to n. So, and then after n it will be give us the sorted one. So, everything we are doing in this array, we are not taking help of any extra array. So, that is why it is called in place sorting algorithm, in place. So, everything is doing in a given array. We are taking help of some temporary variable like key, this I, j index variable, but they are 2, 3, 4. I mean, they are not in the compared to n, they are not order of n something, order we will discuss. So, now we will take some example to illustrate this code, and this is called pseudo code. This way of writing the algorithm is called pseudo code, which is a compact way of writing an algorithm, which is better than the English description. The other way we can just describe what we are doing over here. Okay, take a j, then j you run from 2 to n. So, this way we can have a 2-page description, English description, but that is little bit of boring. So, instead of that we can have a compact way of writing it, and that is called pseudocode. And if we give this pseudocode to any programmer, he or she can do the coding in that corresponding language. Okay, so let us take an example to execute this code. Suppose this is an array which is an input of, and we want to sort this array. So, this is an array and these are the value over here. So, A1, A2, how many elements? There are 6 elements, A1, A2, A3, A4, A5, A6. So, this is a given array, we want to sort it. So, look at the pseudocode of this insertion sort. We start with the jth loop, j is starting from 2. So, this is our j is starting from 2. So, this is our j is starting from 2. So, now we take another index I, which is j minus 1. So, I will be now 1. Now, we compare these two values. Now, if this is greater than, then we do not need to do anything. If this is say 10, then we can increase j to be here. Then still we have this part is sorted. But problem is here, this is less than this value. So, this key value, that means the aj is less than ai. So, this aj is less than I mean AI, key is less than AI. So that means we cannot increase j by this for loop, we have to do some action over here. So that is taken care by this while loop, and also I is not 0, that means we are not yet into the beginning of the array. So what do? We are copying this AI. So this is our AI. So let me remove it. So we are copying this AI, whatever value over here, to AI plus 1. So this 8 will come here, and this 2 is already stored in the key value, so we don't need to worry about losing this 2. And then we decrease I by 1. So now I was 1, now I minus 1 is 0 now. So once it is 0, we stop this, we will not enter into this loop, because this is an ANDing. So either one of is 0, so this is logical operation and AND operation. So if one of this is 0, then we will not enter, and then we will put this key value in, we will come out from this while loop, and this is the instruction, next instruction, we will put a key into the position AI plus 1. So I is 0, AI plus 1 is 1, so we will put this 2 here in this position, 8 is already here. So that will do. So 8 came here and 2 will be inserted here. So that is the first j is equal to 2 loop, and then again j is equal to 3. So this we have to execute, this for loop will go up to n, so up to the end of the array. So now j is equal to 3. So aj is this is pointing, now aj is pointing, aj is this one 4. So we store this value to key, so key is 4, and now I is this one, I is pointing 8. Now this is less than, so we have to compare this, this is less than, so 8 will come here, 4 is supposed to go there, and now I has to decrease by I minus 1, I is 1. Now we compare this key value 4 with AI is 2, we are happy, so we store this over here. So we come out from this while loop, and I is 1 now, so I plus 1 is 2, so we store this key into A2, and this 8 is shifted in here. Okay. So similarly here for next value of j is pointing this one, for j is equal to 4, now I is 3 now. So now we are here, we are lucky, because here when we compare these two, then the key value, this AI, aj is greater than AI. So we don't need to do anything. So automatically j will be increased by 1, and that will be taken care by this for loop. So j is now pointing here. So if you observe, wherever j is, that is the loop invariant, wherever j is pointing, that up to that the sub array is already sorted. So that is the property we want in the jth loop. Now this for aj we need to find the position for aj where we can insert this. Okay. So now we start with this value, this is our new key, and this is our aj, and this is our new I. Now we compare with this is less than, so we copy this 9 over here, and key 3 is already stored in the key. Now I is decreased by 1, again we compare 8 and 3, so again 3 is less than, so we will copy this to here, and now I is pointing to this value 4. Now again we compare this key and AI, and then again it will shift here, 4 will come here, and then I is pointing here, I is 1. Now we compare 3 and AI, but 3 is greater than, so we are lucky, we are happy, so we just stop that while loop, and we come out from this while loop, and we insert this I is 1 here, so A2 we insert, key will insert to be A2, and then j will be increased by 1 by this for loop, and now j is pointing here, this is our aj 6, we will do the same thing, this is our new I, so this is our j now, and this is our new I. So we compare these two, this is 6 is now the key, so we compare these two, this 6 is less than, so you have to copy we have to copy this AI is basically 9 to AI plus 1. So, we will copy this here and then we will decrease I by 1. Again we check this condition, I is not yet 0. Also we compare, this is our new AI 8 and 6. So, 6 is still less than, we will have to copy it here, then I will be decreased. So, we still have to execute this while loop. Now, AI is 4 and key is 6. So, when we compare this will be 0 because this is key is greater than and this is 1, but if 1 is 0 then the ending is 0. So, this is the logical ending. So, we will not go into this while loop and we will directly go here. Now, AI is 3. So, we will put the 6, that is the key value, to AI plus 1. So, 4. So, this in the A4 we are putting this, done. So, this is the execution of the insertion sort. Okay. So, now the question is, what is the run time of this insertion sort? I mean, how much time it will take to execute? I mean, in a computer, say, how much time we can we take to execute this code in a computer or so. So that is called runtime. So obviously the runtime will depend on the input size n. If n is large, suppose we have to sort 100 numbers compared to if we have to sort 1 lakhs numbers. So obviously 1 lakh number will take more time to sort. So that's the reason we want to parameterize. So basically runtime is a function of n. So if you denote it Tn to be the runtime, if we denote the Tn, so runtime Tn is a function of n. So it will depend on the size of the input. If n varies, then the runtime will vary. So we have to make the runtime as a function of n. So we want to parameterize the runtime as a function of n. Okay. Now next runtime will depend on what? Runtime will depend on the, we will come to this, runtime will depend on the type of the input. Because if we have a, say, already sorted element, then that will be easier to sort. So runtime will depend on the time of the input, input pattern. Runtime will depend on the input pattern. So that we will discuss now. Okay, so runtime is depending on the input size. So that's why we want to parameterize the runtime based on the input size. So we write this as Tn. Tn is the runtime of the algorithm when the input size is n. So if we have to sort n element, the Tn is the runtime. It's a function in n. So that's why we want to. This is a function. We can write fn also, but t is the time. So that's why it is convenient to take Tn instead of fn. Okay. So Tn is the runtime of our algorithm when we take the input size to be n. Now the question is, if we fix n, say suppose we are sorting 100 element, we are fixing n. So will the runtime depend on anything else? Yes, runtime will depend for insertion sort. Obviously runtime will depend on the pattern of the input, because runtime will depend on the input pattern, because if we have a, suppose input is a sorted one, input is a sorted array 2, 4, 6, 7, 8, 9. So for this, what if we run the insertion sort code, what we will do, we will compare this and we stop. We compare, so very less work we are doing over here, just for each element we are doing one comparison. But on the other hand, if we have a reverse sorted array, then everybody has to come forward to the beginning in that jth loop. So runtime will be, so time, number of comparison will be more if the array is reverse sorted compared to if the array is sorted. So that means runtime will depend on the input. So that's why we want to have a analysis, 3 types of analysis we will do: worst case analysis, best case analysis, average case analysis. So, this is the worst case scenario for insertion sort, if the input is reverse sorted, because in that case everybody has to come to the beginning of the array. So, that is the maximum work we have to do. So, that will be the maximum runtime for an input of size n. Okay. Because other input, for other input is like not that reverse sorted, then it will take the less time. So, the for insertion sort, worst case is when the input is reverse sorted, and the best case will be when the input is sorted. But we want to have a guarantee, so that is why we will go for, usually we will go for the worst case analysis. So, let us talk about the type of analysis we will do for our algorithm. So, first one is worst case analysis, that is usually we will do, because that is the guarantee. So, worst case means Tn is the worst case runtime means, so Tn is the maximum time our algorithm can take to run the code for any input of size n, for any input. So, that is the guarantee. So, that is the maximum time. So, if I say I have a piece of code, if I say my worst case runtime is 100 seconds, say for example, that means what? That means that is the maximum runtime. It may happen that for some few input it is taking 10 seconds, but I am giving you the maximum one, guarantee one. So, that means you cannot come with some input where it will give you more than 100 seconds. So, it is kind of guarantee. So, that is why this is the usual analysis we will do for algorithm, for any piece of code. And another case is best case. Best case means sometimes for certain input, like for insertion sort, when is the best case? When the input is sorted. In that case, we are doing the very less work. Everybody is just comparing once. So, every element. So, that is the, but the input should be sorted. If it is nearly sorted, then maybe it is less work. So, but it is not for all the it is not a guarantee like here worst case for any input. So, it is my runtime is good, my runtime is say 10 seconds, but if the input is this, if the input is sorted. So, that is really bogus, that is really cheating. So, if I suppose there is 2 pieces of code, sorting code 1, code 2, both are sorting code. Now, if code 1 I design and and code 2 my friend design, and I tell to the competitor that hey, this is my code and it is running perfectly well, but you have to give the input like this, input pattern I am telling you. And my friend is telling, okay, this is my piece of code, my worst case runtime is this 100 seconds, and I am telling my best case runtime is 10 seconds. So, I am cheating because I am not telling my worst case scenario. So, what competitor can, what the judge can do, judge can run my code for all possible inputs and can come out with where my code is performing bad. So, automatically judge can comes the maximum time for my code. So, that is that's why the worst case is the usual analysis one should do for any piece of code. And another one is average case. Average case, for average case we need to take the distribution of the input. We need to assume that the input is following some distribution. Based on that, we have to find the expected runtime. So, this kind of analysis we will do for randomized version of the algorithm. So, we will discuss this when we talk about randomized quicksort. So, randomized version of the algorithm we will discuss this average case, but there we need to take the expected runtime, expectation of this. So, this we will discuss. Okay. So, this is the 3 types of analysis we will do. So, mostly we will go for the worst case analysis, because that is the guarantee, that is the maximum time our algorithm can take for any input, that is very important. Okay. So, now suppose, so what we have learned? We have learned the runtime is depending on the size of the input. If the input size is more, then the time will take more. If the input size is less, then the time is less. And runtime is depend on the input pattern. So, if the input is for insertion sort, if the input is reverse sorted, that is the worst case input, and in that case we will have to the runtime will be more. So, Tn is the maximum runtime for that. Now, suppose we fix these two parameter, like we fix n, suppose we are sorting 100 elements and we are considering the worst case, that means our input is reverse sorted. Now, the question is, will the runtime will depend on anything else? So, what is the answer? Will the runtime depend on anything else, like other than this input size and this worst case input? Yes, it will depend on the computer where we are running the code. So, suppose we are running the code in a brand new computer like this code due processor, and we are running the same piece of code with the same input, which is reverse sorted, it's for insertion sort, and same size 100 element in a very old machine, Pentium 1. So, obviously which one will take the less time? This code due processor will take the less time, because this computer, it will depend on the speed of the computer, because it will calculate faster to compare two element, to do the assignment, because its adder, multiplexer all are very fast. First execution will do there. So, it will depend on the speed of the computer, the runtime. So, now question is, how will judge two piece of code? We have a code 1, we have a code 2. Now, how will tell that which one is good, which one is better? We consider both the code 1, code 2 in the worst case. Suppose we have two code where the worst case is reverse sorted, and we fix the input size, then how will judge? Then we have to run this code in the same computer under the same environment. That is very difficult to produce, because if we are running my code in a daytime and my friend code in a night time, and it is summer. So, daytime the CPU will be busy with some work with the fan speed, all these things. So, definitely my code will be little bit slower through my friend. So, it is very difficult to judge two piece of code, to run two piece of in the to provide the same running environment. So, for that reason we want to get rid of from this machine dependence things. So, that means we want to see the growth of the runtime as n is large. When you go for n is large, then all the machine dependent terms will be can be ignored, because those machine dependent terms will be coming for lower values of n. But if you go for large n, then those terms can be ignored. So, that is the concept of asymptotic analysis. So, basically to ignore the machine dependent constant. So, we will discuss this in more details. We will define three asymptotic notation. So, first one is BIGO notation. So, here is a little maths here. So, this is this is the definition of BIGO notation. So, what do you mean by BIGO of Gn? So, it is a set of all time complexity Fn, set of all function Fn, such that it is bounded by Gn with a constant fraction. This constant is positive constant when n is large. So, that is why there should exist a n0 and a constant, positive constant c, such that for all n greater than n0, that is the way to define the limit n tending to infinity. So, this is for large n, this means for large n. So, we just if Fn is less than c of Gn, then we say Fn belongs to BIGO of Gn. So, this is the definition, mathematical definition. For example, if this is our Fn, we want to see whether this is BIGO of n square or not. So, to show this is BIGO of n square, this is our Fn, we need to show this is less than some c n square. So, for that we are trying this. So, we just take this one, this is less than 100 n square, and this is plus 20 n square. So, this is 2 is missing over here. So, this is 20 n square, 20 n square plus 5 n square, because n is a natural number, n is the number of input, the array size. So, n is a natural number. So, n start from 1, 2, 3 up to this. So, n is greater than equal to 1. So, this condition is satisfying. So, this is basically 125 n square. So, our C0 C is 125 and this is true for any n greater than equal to 1. So, n0 is 1 over here. So, we just prove that by definition this is a big O of n square. So, as an exercise you can just try at home. This is big O of n and this is big O of n cube. So, the next definition is notation is big omega of big omega notation. So, big omega of Gn. So, this is a set of all functions Fn, set of all time complexity such that which is bounded below. So, this Fn is greater than equal to Cgn when n is large, n is tending to infinity. So, that means there should exist n0 and c which is positive constant such that Fn is greater than equal to Cgn. So, usually we go for the big O because big O is the upper bound. Like if I say my time complexity is less than n square, like my code will take the time 100 less than 100 seconds. And if we say this my code is taking greater than 50 seconds. So, this for time complexity we usually go for big O, but this big omega will help us sometimes to know how much minimum time we can achieve. For certain algorithm we can show that we cannot go beyond n log n. Like for example, for comparison based sorting algorithm we cannot go beyond n log n. So, those to show those things we need help of big omega notation. So, big omega is this definition is this one. So, to show this is big omega we take this value, this is our Fn. So, this greater than equal to 3 n because we are ignoring 5, and if we take this to be n is greater than 20, then we put it n over here and this is minus. So, this will be greater than 3 n cube minus n cube. So, this is 2 n cube. So, that means our C is 2 and n0 is 20 and this is greater than equal to C n cube. That is the definition. So, that means just now we have proved that this is big O of big omega of n cube. And similarly, you can do this exercise. This is big omega of n, this is big omega of n square. Now, if we combine this big theta, big O and big omega, that will give us a big theta. So, this is both side bounded. So, big theta definition is if for large n tending to infinity, that means we should have n0 such that there should exist two constants. So, this is basically this part is giving us big O and this part is giving us big omega. So, this is the both. So, this part is our big O and this part is our big omega. So, if Fn is both big O and big omega, then we say this is big theta of Gn. So, for example, we can show this is a big theta of Gn because we can prove this is a big O of n cube and also we can prove this is a big omega of n cube. So, finally, we can show that means it is a big theta of n cube. So, but if you want to ignore these maths, you can just do like this engineering sense. This is the engineering sense. Suppose we have a time complexity like this, Tn is this. We have a sorting algorithm where this is my time complexity, this seconds. Okay. Now, what we do? We just ignore all lower order term. Here higher order term is n cube. So, other than n cube all lower order term. We drop all lower order term. So, we just cancel all these terms. So, these terms we cancel, this term we cancel, this term we cancel. Then finally, we have 3 n cube. Then we ignore the leading coefficient 3 and that will give us the order, and that is basically big theta of n cube. So, this is the order of n cube algorithm we can say. So, that is in engineering sense, but we do have a mathematical definition of big theta of n cube. So, that we have discussed. Okay. So, now we have to analyze the quick, because we want to see why it is important, asymptotic performance, because asymptotic performance can tell us whether the order of n square algorithm is better or order of n cube algorithm is better. For example, suppose we have a two piece of code and one code is giving this time complexity, this second, and these all these 90, 50, 60 they are coming from the machine dependent terms. That means how much time it is taking by our where we are running the code, adder, multiplexer, our gates are taking how much time. So, these terms are all machine dependent terms. And we have another piece of code where time complexity is this one. So, this may be a brand new laptop where this machine dependent terms are less because it will compute very fast. I mean, as multiplexer, all these things will take better time than this. Now, which one is better? Now, if you draw the graph, this is our T2 and this is the Tn and this is n. So, for lower values of n is may mislead us because lower values of n, this is better, T2 is better. But if you take the higher values, if you observe this run time for large n, we will say, see after some point of time, this T1 is the better run time, because T1 is order of n square algorithm and T2 is order of n cube algorithm. So, obviously, order of n square algorithm is better than order of n cube algorithm. So, to see that, we have to see the growth of the runtime as n tending to infinity. In that sense, we can ignore this machine dependent constant, and that is the way we can get rid of from machine dependence time, like how much time our adder is taking. We just count the how many comparison we are doing, that is all. We don't really, because it is difficult. I mean, then you have to go for the exact time how much our machine is taking. So, that exact time comparison of two code is very difficult, as we cannot provide the same environment of running these two piece of code. So, that is why we go for asymptotic runtime. Asymptotic, we want to see the order of the runtime, whether it is order of n square algorithm, whether it is order of n cube algorithm, whether it is order of n log n algorithm, that we want to see. Okay, so now we want to analyze the insertion sort with the help of this asymptotic notation. Okay, so this is the insertion sort analysis. I mean, we want to compare the we want to find the runtime of insertion sort. So, we will just first see the insertion sort code and then we can come back here. Okay, so for insertion sort, we are talking about insertion sort time complexity. So, let us bring the pseudocode. So, this is the pseudocode for insertion sort. Now, here we have a loop in J. So, this size is order of n, this loop size. So, that is why Tn is summation of j is starting from 2 to n. So, depending on what is the work we are doing here. Now, this how much time it will take for this assignment. So, this assignment, this is we are assigning the value of this aj to a temporary variable key. So, this will take constant time. I mean, that is why it is theta of 1, because here we are talking about asymptotic sense. So, we are not really bother how much exact time it is taking for doing this. So, that is why it is theta of this is taking theta of 1 time. So, constant time. So, this is basically theta of 1. Theta of 1, and we have this is also theta of 1 or constant, some constant time, and we have a loop over here. So, this loop is while loop, and this loop will go, worst case it is a reverse sorted. For reverse sorted element, each key has to come to the beginning. So, size of this loop will be order of j. So, that is why this is order of j. So, it is, and then again inside this loop whatever we are doing is again theta of 1, but size of this loop is order of j. So, total time is theta of j, order of j you can say, because these are the assignment. This I is equal to I is assigned to j minus I minus 1, and to checking this I is greater than 0, to check this. So, that is why we will take this away. This is a some constant time, it is theta of 1 asymptotic sense, because we do not really want to bother about the exact time, exact computer time, because we are doing the asymptotic analysis of this asymptotic notation of this time complexity. So, this is theta of j, because j times we are doing the theta of 1, theta of j, and again this is theta of 1. So, this is basically summation of this, and this is order of, this is arithmetic series, this sum, summation over 1, 2, 3, or not 1, 2, 3, 4, 5 up to n. So, this is n into n plus 1 by 2 if it is starting from 1. So, this is basically order of n square algorithm. So, this is worst case when the input is reverse sorted. Now, average case is, for average case we need to assume all the input is equally likely, all the possible permutation of the input are equally likely. So, there we can assume that on an average, although for average case we need to take the expectation of the runtime, but here intuitively we can say on an average every element, for jth loop, every key every element is coming halfway to the beginning. In the worst case it was coming all the way to the beginning, in the average case half, that is why it is j by 2. So, on an average this is j by 2 or summation of j is equal to 2 to n. So, this is also half of n into n plus 1. So, this is also order of n square algorithm. So, for insertion sort, worst case and average case both are order of n square. And what is the best case? Best case is if the input is already sorted. In that case, what is the time complexity? It will be summation of j is equal to 2 to n, and we are just comparing 1. So, theta of 1. So, it is order of n. So, insertion sort best case time complexity is order of n. So, now the question is whether it is a fast sorting algorithm. Well, it is worst case it is order of n square, because we do not have control on the input could be anything. So, but best case is order of n, but that is only possible if the input is sorted. To get that input, it is quite I mean it is, if we give that particular input, then we will get the best case, otherwise it is for any input we will not get that order of n. So, it has been observed that for low value of n this is performing good, and for large value of n it is not good, because it is a order of n square algorithm. So, now we want to learn a better algorithm than this, which is called merge sort. So, that will give us the worst case time complexity order of n log n. So, that we will see now. Okay, so this is a merge sort, which is another sorting algorithm we want to discuss. So, in merge sort, what we have given a array as a input of n numbers. So, we have a array of n numbers starting from 1 to n, and what we are doing over here, this is divide and conquer approach. What we are doing, we will talk about divide and conquer approach in lecture 3 in more details. Divide and conquer approach means we have a problem of size n. This is a sorting problem. So, we have an array of size n to be sorted. So, this array, what we are going to do, we divide this problem into sub problems. So, this array we divide into half. So, this is n by 2, provided n is even number. So, that thing we are assuming, because ultimately we are going to discuss the time complexity for large n. So, asymptotic sense. Okay, so, what we are doing here, we divide the array into half, then we recursively sort this subarray, this subarray. That is the recursively we are calling the merge sort again on this subarray, we are calling the merge sort. So, that is we are reducing the problem into sub problems. So, our problem was sorting problem to sort n element. Now, we have a problem reduced to sort n by 2 element, and here also n by 2 element. So, we recursively sort this subarray and this subarray by recursively calling the same merge sort. And once we have a solution of this, so this subarray is sorted and this subarray is sorted, then we call a merge subroutine, which will take this subarray as a input, and which will give us a sorted whole array. So, that merge subroutine we will discuss soon. Before that, let us just discuss what is going on over here. So, once we in the first level, once we divide this, then once we call the merge sort on this, again it will divide into sub-subarray. So, again it will divide into half on this subarray, n by 4 n by 4. Again this will be divided into n by 4 n by 4. So, this will continue until we reach to 1, until the array size sub array, the array size reach to 1, because once it is reached to 1, then that is sorted, because only one element it is sorted. So, we have one element here, one element here, this is sorted, then we call the merge and it will give us a that corresponding sub array. Then we have a sorted sub array, we call merge, this way we go and ultimately we reach here. So, that means we have a this will be done by recursive calling. So, recursively we call the merge sort on this subarray to sort it, we call the merge sort on this subarray to sort it, and once we got a sorted subarray, we call the merge to combine these two sorted subarray to get a sorted whole array. So, that is basically the merge sort. So, we stop if n is equal to 1, because n is equal to 1 means only one element that is sorted. Okay. So, this need the n to be a power n to, if n is a power of 2, then we can keep on divide, then you will get the integer, otherwise we have to do the lower ceiling of this, I mean the integral part of this, but eventually we will be doing the asymptotic analysis. So, for large n, so we can just ignore that part, we can just assume that n by 2 is a integer. Okay. So, this is called merge sort. Now, we will discuss the merge subroutine, then we go for the time complexity of this algorithm. So, in the merge subroutine, what we are having? We have two sorted subarray. So, we have two sorted subarray. This is the given array, and we have call the merge sort recursively. So, this is one subarray which is sorted after many recursive call, and it will eventually give us the sorted subarray, and this is also sorted subarray. Suppose this array contain this number 2, 7, 13, 20, and these array contain so these array contain this number 2, 7, 13, 20, and these array contain this sorted number 1, 9, 11, 12. Now, we want to merge it. We want to call the merge subroutine to get a whole array. Now, to do this, we need to take help of a extra array of size n, of same size. Otherwise, we cannot do it in the same array with the time complexity. We want this merge to be done in linear time, order of n time. So, so that's why we need to take help of a extra auxiliary array. So, we take a auxiliary array over here. So, that is our auxiliary array, where we will store the sorted one. So, what we do? So this is the first element. So, this is 2, and this is the first element on this. So, these are the least element, because this is sorted. So, we have least element over here. So, we compare two least element. So, this element we compare. So, then we return the minimum one, I mean the least among these. So, if we compare these two, minimum is 1. So, we return 1. So, we are going to return this one will be copied here. So, we will copy 1, and then it will point to the next minimum over here. So, this way we continue, and we will keep on storing this auxiliary array in a sorting way. So, this will be output, this will be stored in the auxiliary array, and then the next minimum is 9. So, this array, this sub array minimum is 2. So, we compare these two. So, 2 is the minimum among these two minimum. So, we return 2. So, then we take 7 as the next minimum after returning 2, then we compare these two. 7 is the minimum among these two. So, we return 7. So, then after returning 7, it will point to the 13. So, 13 is the next minimum. So, then we compare 13 and 9, 9 is the minimum. So, we output 9, and then we point to the next minimum 11, and this we are doing in this auxiliary array 11, and then we compare 9 and 11 and 13, 11 is the minimum, we output 11 onto that auxiliary array, and then 12 we point 12 and 13, 12 is the minimum, we output 12, and once one array is exhaust, we just output the remaining element of the other array. So, we just output 13 and 20, we just copy 13 and 20 in auxiliary array. So, this is the merge subroutine what we are doing over here, we have illustrated through an example. So, how much time it is taking? If this is n by 2, this is n by 2, if the total array is n, so this is n by 2, n by 2. So, time is taking basically n, because every time we are comparing one and we are storing one element. So, there are n element to be stored and we are comparing one. So, this comparison again we are assuming the time to asymptotic sense. This comparison we are not bothering about exact time to compare this, how many second, how many millisecond. So, this compare is a constant time. So, theta of 1. So, theta of 1 time we are spending for each comparison, and there are n comparison we are doing, because every time we are returning, we are storing one element into the auxiliary array, n element need to be stored. So, this is basically theta of n. So, this is what is called merge subroutine, and this is the time complexity theta of, it is a linear time algorithm, okay, because this is theta of n, and this to achieve this by linear time, we need to take help of the auxiliary array. If we want to do it in the same array, we cannot get, you can think of this to by doing this in the same array without taking help of any auxiliary array, but that cost will be more than linear. So, that you will not get in linear time theta 1. So, I suggest you to think about it. Okay, then come to the time complexity of merge sort. So, this is the time for merge subroutine. Now, we have to get the time complexity for merge sort. Okay, suppose Tn is the time for merge sort for n elements. So, for this A array, n is the number of input, number of element to be sorted. So, Tn is the time, we need to get the value of Tn. Okay. Now, we need to we have to get the time for each step. So, this is theta of 1, because this is just an assignment, again in asymptotic sense this is a constant time. So, theta of 1, and here we are applying two merge sort call. Okay. And what is the size of these two call? I mean, we have two sub array, this one we have two sub array, this is n by 2 and this is also n by 2. Okay. So, we are calling merge sort on both the sub array, this is n by 2 and this is n by 2. We are calling merge sort on this two sub array, and that will be, if Tn is the time for merge sort, if n is the input, then for n by 2 input it will be Tn by 2, and this is sequential execution. It is not parallel, that if we have two computer, we can ask one computer to execute this, one computer. So, that is parallel computing. But here in this algorithm course, we will be doing sequential computing, means we have only one processor. So, that means we have to complete this job, after that we can complete this job. So, to complete this job, the time is Tn by 2, and then we have to complete this job, which will be Tn by 2 again. So, that is why it is 2 Tn by 2. So, 2 times we are calling the merge sort on these two sub arrays of equal size. Okay, here n is, so we are assuming this is integer, otherwise we have to put the lower ceiling, and for asymptotic for large n we can assume this is okay, these two size are same, otherwise one may be if this is k size, this may be k minus 1, but that is k minus 1 is lower ceiling or upper ceiling. So, and this time is theta of n, so the total time is sum of all these. So, this will be this theta of 1 plus 2 theta of 2 t of n by 2 plus theta of n, these two will combine to theta of n. So, this is the recurrence relation of the time complexity of March sort. Now, we need to solve this recurrence. So, how to solve this recurrence? So, this type of recurrence we will be getting for different algorithm. So, the question is how to solve the recurrence. We will know 3 methods in the next lecture to solving the recurrence. Among them, one method is recursive tree method. So, that we will talk about now. So, in a recursive method, this is the recurrence. So, what we will do? This is Tn. So, Tn is divided into 2 parts, half. So, we need to sort this subarray, then we need to combine this with a cost this March Cn, and then again this is a subarray of size n by 2, again it will be divided into n by 4, again this is the cost for merging, I mean this combining. So, that is the cost, and this way we continue until we reach to n is equal to 1. Once we reach to n is equal to 1, we stop because that is sorted, and then we go back by merging this. So, this Tn is the sum of all these nodes in the tree. So, how to get the sum? We have to find the height of this tree. So, height of this tree is basically log n. Why it is log n? Because the way it is coming down, this is n by 2, n by 4, this way it is coming to 1 size. So, if the height is h, then n by h is equal to 1. So, n is equal to 2 to the power, n by 2 to the power h is 1. So, n is equal to basically 2 to the power h. So, h is log n. So, this way we can just do the sum of, so to get the total sum we can do the level wise sum. This level it is Cn, next level also it is Cn, next level Cn. So, this way we can continue and we can see the number of leaps is n, and so the next last level also Cn. So, if we add it up we will get total Cn log n. So, this is a order of n log n algorithm which is better than the March sort. Now, the question is this is March sort time complexity which is better than the order of n square algorithm which is insertion sort. So, now the question is which one is better. So, to conclude that because March sort time complexity worst case is order of n log n and insertion sort is order of n square, but March sort is not in place sort. For March sort, for March subroutine we need to take a extra array to store the elements. So, that is not in place, whereas insertion sort is in place. Everything we are doing in that array given. So, that is one advantage of insertion sort, but if we compare to the time complexity, then March sort is better because it is a order of n log n algorithm in the worst case, and insertion sort is order of n square algorithm. But this effect will come for large n, because if we take the small n like n is less than 30, then we may not get this, these two may be similar, because in that case n and log n may not be having, but although log n is much lesser than n, because you say if n is 2 to the power 10 which is huge number, then log n is just 10. So, log n is much lesser than n. So, this is asymptotically this is a better algorithm than order of n square. So, I suggest you to do this code, both the code, and you just get the time, maybe system time, and you check which one is giving less time, run time for different values of n, and you will see this result. Okay. So, this is the end of lecture 1. In lecture 2, we will discuss the how to solve the recurrence. So, thank you.